Good morning. I hope you are quite awake. Maybe I'm not. This is a lecture. This is not a seminar. So I'm going to tell you basic stuff that I think, and I wonder why not. I think it should be more diffused in the community of science in general. So this is general techniques that are so important that I think everybody should be taught these very simple things that I'm going to talk here. At some point, it's going to get a little messy. Since it's a lecture, I'm not going just to show you little pictures of mice in color. So do not expect that. I'm going to do mathematics. And I'm going to do it. It's a lecture. That's my last apology. Okay? I'm going to tell you about information, and I'm going to tell you something that it might be surprising, which is why, when we deal with situations in which information is not complete, we have to use ideas of probability. Essentially, there is no way out. We either use probability or we risk doing nonsense. That's the main message of this lecture. And then if I have time, if that's not enough, I'm going to tell you why probability and entropy comes along. I'm going to do some applications, and I'm not going to have time to go into all the applications I would like to tell you about. So this is something that you don't get every day. It's why do we have to use a given mathematical structure and risk doing nonsense if we don't? So it's really a bold statement. First of all, people learn about random variables, random phenomena, and they think that there's this class of things that are deterministic, which are governed by Newton's laws, for example, and then this other stuff that is really random, truly random. And what is the main example that you can teach a child about randomness is you get a coin. Do you have a coin? I forgot to bring my experimental demonstration. No coin. Anybody has a coin? A coin? No, a coin. What? A pointer? No, a coin. Okay, we have a coin here. Oh, thank you. I'm going to do an experiment. I'm going to throw this. And I'm going to pay, if you are willing to bet, 10 reais if the number comes on top, and I'm going to want 1 real if the face comes on top. Are you willing to do that? This is a simulation. If you control the angle of in which you throw the coin and the height, and that's blue are for tails, white are for heads. Are you willing to bet with me 10 to 1? You get 10, I get 1. Yes. Okay, I threw it once. It fell, and it can be described very precisely under the influence of gravity, and we can describe that using Newton's laws. We can integrate them. This is a deterministic problem. It doesn't need any probability. We can calculate it. Actually, I managed, now this is a much lower height, and I managed to be on this region. In that region, there is nothing to do. There's no probability. When does probability come into being? Well, if I throw it like this, and I'm not playing now. If I throw it like this, then I'm in this region. And what is the randomness that I should be attaching to this coin? It's not in the fact that it was, in the previous experiment, moving along according to Newton's laws, and now it's not. No, it's still moving along. It's the same Lagrangian, it's the same force, it's the same equation. But now we're in a region where the control I have on the initial conditions in this coin are not sufficient, are not sufficient to make to choose a white region. So if the control I have in my hand is about this much and this much. So I'm in a region like this, and yes, I don't have information about the initial conditions, and so I don't know how it's going to land. So coins, you see, when you do physics, you learn that, there is the charge of the electron, there is Planck's constant, you have the speed of light, you have these fundamental constants, but 1/2 is not a fundamental coin that comes with an elementary particle known as coin. Okay? So this is the main I think it's a main point that people think that 1/2 is something, it's a fair coin. As if fair coins, as if coins could be fair or not. Coins are just objects subject to the laws of physics that we know. And I might be fair or not. And that's what you might say that I was not when I chose the conditions of the experiment. Okay, so now I'm going to give this back. Yeah. I said I don't have complete information about the initial conditions of the coin. Let's go to a simpler problem. I'm going to be talking about assertions. What is an assertion? An assertion is the mass of Saturn is in this range, given range of masses, or any parameter of a theory is in this region, or it's raining. It's an assertion. It's a phrase to which you can, or we're willing to give a degree of belief whether it's true or not. So we're going to talk A, B, C, D are assertions. And I'm going to tell you, information is something that can be written like this. A is true. And we want to discuss our beliefs about the truth of assertions when we have information. And I have not defined information, and I'm going to do that. We defined assertion C by A implies B. And I'm going to use this notation, B, given that I know A and C to be true. I suppose A and C are true, and then I want to discuss what do I believe about B. And if A implies B and A is given, then I have complete information about B. And if B is not true, I have complete information about A. I know it's false. So these are cases in which we don't know, we don't need anything else. We know everything. This is complete information. But if there is something like complete, there must be something incomplete. And this is a case, we are in the same problem as before, but now I tell you that B is true. What can you say about A? And I tell you that A is not true. What could you say about B? These are really not in what Aristotle could argue to be logically clear. Yeah? Let's have an example. Suppose I say that A means it rains. B, there are clouds. And given our experience, given the amount of physics that we know, we can say that, to the best of our knowledge, A implies B. What does A implies B? It's logical implication. So it means that if it rains, there must be clouds. That's something that we know. Note that physical causation is the other way around. It rains because there are clouds. But logically, we can only conclude that there are clouds because it's raining. The other way around. Okay, the questions that I say I have incomplete information are this type of questions. Is it more likely to rain because there are clouds? Or is it more likely not to be clouds because it's not raining? Yeah? What can we say about this? And the answer to both questions is yes. We are supposed to believe more in rain if there are clouds, and we are to believe less in clouds if there is no rain. Can you prove that? How can you prove that? That's the exam you're going to have to take on Sunday. Yeah? We're going to do it here. So we're trying to build, this is, okay, so at this point you say, yes, it's probability. And I say, why? Why is probability? I don't like probability. Actually, I'm going to tell you the story of a professor in, Yale, in the 1940s, which he looked at this problem and he said, I don't like probabilities. I don't want to use probabilities. So what am I supposed to use? And he said, let's construct a theory that satisfies certain desiderata. Desiderata are my desires for a theory. So I'm going to say, this is a desire that I wish my theory complies to. Then I'm going to throw away all the theories that do not comply to that desire. So I say, I'm going to build a structure to comply with my desires. It's totally different as when you learn in a physics course. You say, well, if this falls, we have the mathematical theory, and then from the mathematical theory we deduce all the properties of the motion. This is different. I'm going to think about simple cases. These simple cases impose constraint on the theories, the mathematical structures that I have to deal with, and I'm going to throw away all the theories, and I'm left with something. And what is this something? It's the mathematical structure that I wish to tell you about. Of course, if you're free not to use that theory, but then you're going to be violating one of these desires. I want to know, like in the previous transparency, I use the word more likely. More is something that is linked to language. I say, I like this more than that. I have preferences. I have to decide on something. I have to state my preferences and then act according to some principle of maximization of something, my preference. So if I say that something is more likely to be true than something else, my desire is to represent that with a number. So the belief about the truth of A when C is known is going to be represented by a number. At this point, you must be saying, I should have stayed in bed. I shouldn't have come. Yeah? Because could anything be more trivial than listening to this guy saying that I'm going to represent this by a number? Well, if I tell you that instead of a real number, I chose a complex number, then I would deduce quantum mechanics and Schrödinger equation. So this is not a trivial assumption. It's something that I do because I want to say I believe more in rain, given that it's clouds or not. But it has, if I'm going to order things according to my preferences, I might get into problems if I don't use real numbers. So I'm going to use real numbers here. And this is my desire. So any theory that deals with incomplete information and cannot be translated into numbers, real numbers, I don't like. I'm going to throw away. It might be useful. You might say, I have a gut feeling for this. Or you can throw buzios. I don't know how you say that in English, but buzios. You can throw dice. I don't know. I mean, you can do your own theories, but I'm going to use numbers. So, if I believe more in A than in B, when I know my background information is D, and I believe more in B than in C, then I want immediately to believe more in A than in C. And that is only, it's naturally satisfied if I choose to describe these objects with numbers. Well, we don't speak, you see, for those in biology, and for those in physics, which is 99% of the audience, there is a real puzzle, which is, why is mathematics capable of describing nature? Why is it useful to describe nature? That's also going to be asked on Sunday. I don't know. But I think it's a language. It's a language so precise that allows us to make precise statements and check them and see what we're saying. But we don't speak like it rains. There are clouds. We say things like, it's raining and the stock market went down. So we have conjunctions, conjugate and subordinate assertions. We have ways of composing more complex assertions given simpler assertions. And I only need to look at two of them. I'm going to look at the disjunction and at the conjunction. This is or and. So I'm going to look at the phrases that I can make by saying phrase A or phrase B. And this is something that is going to be true if only one is or both are true. And I'm going to say A and B, and this is true only if both A and B are true. And this is, for obvious reasons, it's called the sum, and this is the product of logical variables, okay? So we can make complex assertions by joining things together. We have other connectives. We have the negation, and we have XOR, and we can build lots of things, but this is sufficient. Once I make complex phrases, such as this, I want theories, mathematical structures, that can help me get numbers for these assertions in terms of simpler assertions. Which are the simpler assertions? Well, you see here, this is a really obnoxious behavior. I'm always going to write, except at one later transparency, it's something given C. So C. You could say, why does the guy always write C and C is not doing anything? It's always given C. In every assertion here is given C. It's the background information that you have. It's everything that you know that is relevant to this problem. And it's not changing at this point. Yeah? So C is given. So if I want to discuss A and B, I want to discuss theories for which there is an F, which might be a function of A, of B, of A given B, of B given A. Maybe not all of them, but if something is complex and I want to analyze it, it has to be in terms of the assertions that I can build with the atoms of this assertion. of all of them? I don't know. What is F? I don't know. Okay? So what I'm saying is, if you're going to analyze something that is complex, it has to be in terms of the simpler assertions that can be built with the atoms, both for the sum and for the product. So I introduced two functions which I don't know what they are. And I don't know, I wrote it as a function of 4 variables, but I don't know if the 4 variables are needed. Okay? What I know is that there is not much else that I can put here in order to make a sensible mathematical structure for this. So neither F nor G are known, and maybe they're a function of a subset of these numbers. And then this is the crucial ingredient. My third desire. My third desire is to throw away all the theories that do not comply with this simple requirement. Suppose I have a complex assertion, and I described it in terms of the atomic things that I can build. If it's complex, I can analyze it maybe in different ways. Whatever way I do it, at the end, they have to give the same result. So I cannot assert my belief in A or B in one way, or in another way, and come up with different beliefs. They have to be the same. This is really something so basic that if you do not believe that it should be like this, then we are really different people. Okay? But anyway, you see, we are both constructed by natural evolution, so I believe we're more or less the same. Yeah? This does not, I call this a consistency desire. But this is, because otherwise it would be obviously inconsistent. But of course, I cannot guarantee consistency. I can only guarantee lack of consistency if I do something that goes, in one analysis goes one way, another goes another way, and it doesn't fit at the end. Okay, that's it. From 3 blah, blah, blah desires, I'm going to get probability theory. So it's not like I'm postulating, these are the axioms of probability theory. I'm saying, I don't know what I'm talking about, but I wish to talk about something that uses numbers to quantify degrees of belief, that has 2 unknown functions, f and g, for analyzing more complex assertions. And if I do it in one way and do it in another way, well, it has to give the same result. Okay? So I'm not telling you this is a sigma algebra and I'm talking about, no. Okay? So at this point of the lecture, does anybody disagree that these are reasonable desires? I would love to see anybody disagreeing and after the caipirinha wears off, yeah, from yesterday. But this is it. That's really important to know. That's it. From these 3 desires, I get probability theory. And a little bit more. So we have, this is a joke I always make. If this were enough, then Euclid wouldn't have to write a big book after he wrote the postulates and the axioms and the definitions. Yeah? It's just 2 pages. Why did he write 500 pages after that? It's not, you have to put something. Okay. That was the fun part. Now we have to, yeah, do like this and move like that. This is something you can try. Suppose these are Boolean variables, and I say A or B. And you see, I have 8 possibilities for A, B, and C. It can either be true or false, true or false, true or false, 8. The truth value of this is exactly the truth value of that. If I do the the disjunction of this first and then of the other, or if I do this and that. It's the same. Now I'm going to, what do I want to do? I'm trying to analyze what should the function f be. Remember I introduced two functions, f for the sum, g for the product, and I'm going to look at this. First, we're going to look at A and B, at two that are mutually exclusive. What is mutually exclusive? That they cannot both be true at the same situation. I'm not going to use the word at the same time because I don't believe that time exists as such. So it's not an assumption I'm making that time exists. There are different states of knowledge, yes, but okay. Mutually exclusive means that if I'm doing experiments in which the dice falls in one phase but not on two phases at the same time. So number 2 and 5 cannot be true at the same time. Only one of the phases. I use time because but I didn't want to. So mutually exclusive means that A given B and B given A is some number. What number? At this point, some of you are willing to say it has to be 0. Because if B is known to be true, then I know for certain, this is certainty, that A is false. And at the same token, if A is known to be true, B cannot be true. So this is absolute certainty that it's false. This is the number that represents absolute certainty that it's false. I call this absolute certainty that it's false VF. I don't know the value of VF. I'm going to deduce the value of VF. The function f that I had possibly could depend on 4 arguments. But now 2 of these arguments are false. Okay? You see, it had this false, this is A given B, B given A. These are known to be the same value and the same value for false, although I don't know the value. So this is not a function. If I change A and B, these things do not change. So this is not a function of 2 arguments, it's a function of only 2 arguments. Okay? Okay, so now I look at A, B, and C. So this function of 4 arguments is now, I have to lead only with functions of 2 arguments, which is easier. And then I'm going to, once I do this, I'm going to consider any A, any B. So this is the assertion that C is true given D, but this is a number. So this function, if I'm looking at this is a function of numbers. So the argument of a function is a real number. The real number represents my belief that something is true. What is true? An assertion. In what conditions? Conditioned on some other assertions. Okay? Now, I'm going to get this A, B, and C, and I'm going to look at A or B or C, or I'm going to look at A or B or C. But since these things are the same, this is just that. If I look at this is the OR statement, which you see, I get this part here. This is f. It's a function of 2 arguments, and this argument comes here. But if I look at this part here, then I have f of A, and then f of B or C. And they must be equal, because I'm remembering that I demand not to be manifestly inconsistent. But A or B is again an f function. And B or C, it's again an f function. So this equality here is this one. And then I have f of of A given D, of B given D, of C given D, of A given D, and this is an F function of B and C. Okay, so you see, I started blah, 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 but now I'm getting equations. And this is an equation which is, if I substitute now for real numbers here. These are the X, Y, Z kind of thing. So I have F of X, Y, Z, F of X, F of Y, Z. This is the associativity equation. There are books written about this. The first one to read this was Abel, Norwegian mathematician who died at 30 few years. And ever since then, this appears everywhere. If you do quantum chromodynamics, it's going to pop up at some point. This is really an interesting equation. What I'm going to do now is to show you what is the most general solution for this equation. This is a functional equation. This is not an equation like, say, x minus 1 equals 0. What is x? X equals 1. It's a number. But this is a different type of equation. This is an equation in which the unknown is a function itself. So this is a functional equation. There are three, at this point, I can take three paths, one of three paths. The first one is to show you, without making any assumptions about differentiability of this function, and I can prove in 120 pages the general solution. The second is to make assumptions that this function is differentiable on all two of its arguments. And then in 3 pages, I can show you the general solution. And the other approach, which I'm going to take here, is to show you the general solution and substitute and see that, yeah, it works. Yes, great. So which one do you prefer? So this has to be, you see, I can change A, B, and C, and they can be mutually exclusive. I can do that. And I can put values of X, which are, I believe very much, values of B, which I believe little, values of C. I can change these beliefs. This has to be for every A, B, and C, mutually exclusive. Okay, so we have an equation. You see, at this point, you must be feeling really secure because I started talking like a lawyer, and now I'm beginning to make sense as a mathematician. So this is something you should, okay. Let phi, I'm going to, this is you see, some of you are not very familiar with functional equations. But I'm going to say, any function phi for which if x is larger than y, phi of x is larger than phi of y. This is called a monotonic function. Why monotonic is interesting for us? Suppose I have beliefs x, y, z, and I apply to these beliefs a monotonic function. Whatever was larger goes to a larger value. Whatever is smaller goes to a smaller value. Things might be changed by phi, but things do not change position in my ranking of preferences. So if I prefer something more and I apply a function phi, I still prefer it more if I compare phi's or if I compare the arguments. Okay? The general function is pick up any function phi to the minus 1, phi, get the inverse function of what argument? The sum of these two. This is the general, this takes in the book by Axel. It gets the proof, it builds on the proof of Abel, and well, it takes 120 pages. This is the most general solution of the associativity equation. And you see, this is something nice about mathematicians. You have strictly larger. If I had strictly larger, instead of strictly larger, I had larger or equal, things would be different. Because And it would be different in a practical way, because things that might be, I have a clear preference of this over that, I believe more in this than in that, they might be mapped to the same point. And now I have confusion. So this is extremely important. Okay, if you substitute this in this equation, you see you get phi to the minus 1 for this f, and then you get another phi, you get phi of something plus phi of something, but what is a something inside here? It's phi to the minus 1, and then comes this z, phi of z, which is this part. And then I look at this part. Then I work on this. Then the phi and the phi minus 1 cancel, and what I get is phi of minus 1, phi of x, phi of y, phi of z. And if I do the same substitution on this side, I get the same thing. So play around with it. It's very easy. Okay? Remember that phi minus 1 of x is just x. So this is the solution. You see, if I apply phi to the minus 1, phi to both sides, I get a mapping, monotonic mapping of this number, and I get equal to that number. So phi of f is phi plus phi. So if I want to, you see, at this point you have to say, what is this guy talking about? What? I'm saying I want to describe beliefs by numbers, but I haven't said anything about what numbers I'm talking about. This is second chapter. Now I just want to establish the structure. I don't know the specific numbers. It's like this institute in a European country which closed because they found the value of x. You know the joke? There's a European country in which that happened. If I had the numbers here, then I would be over, and every theory of probability would be 1/2, like the coin. Yeah? So I don't know what numbers are these. But I don't know what numbers are these. I don't know this function f. But I know that the function, this unknown function, which is monotonic, of this function, which I don't know, of these numbers, which I don't know, is exactly equal to this plus that, which I don't know. Okay? But I know to what I discover. I know exactly how to do this. So the phi value of this assertion is the phi value of this assertion plus this assertion in the case where A and B are mutually exclusive. This is the inverse function of phi applied to this argument, which is the sum of the application of phi to x and y plus y. Okay? So this is something, you see, these numbers I don't know, this function I don't know, but this is a number, and these numbers should be composed as such. Now comes, this is work by Cox, 1946. So you see, in neuroscience, you talk about what came, the students, you talk about what came last year. In physics, you start in the 1600s. And then when they get to the third year, you say, well, yeah, now we're in the 1900s. You should be happy. I'm talking about the 1940s. And I'm going to talk about the 2000s. Yeah. At this point, Cox said, forget about the numbers that I didn't know. I don't want to talk about those. My beliefs are represented by this number. And I should concentrate on deciding what to do with these numbers and how to calculate, how to estimate, and how to attribute numbers to them. So instead of order of beliefs given by an unknown number of A of D, I'm going to talk about a non-monotonic function of an unknown real number phi. Okay? So now, but phi has this very simple property. Okay. Now it comes to the point where I can give you my first number. Say something has this value. If A or B, if A and B are mutually exclusive, then what is this? And C, okay? If C, A, B, and C are mutually exclusive, which is the case that I was looking, then A or B cannot be true if C is true. So this is phi of this value Vf. But this is the disjunction of two mutually exclusive assertions, so it has to be the sum. But this is still false, and this is still represents my certainty that it's false. So this is phi of Vf, and this is phi of Vf. And so I have one of these, two of those. It has to be 0. It could be infinite. But this is just being infinite. If I change the phi and I turn upside down my scale of beliefs, then I'm just fine and I can do it 0. It's an exercise I'm not going to do. And now we did the simple case where things are mutually exclusive. Now I'm going to look at the general case. How these belief numbers behave when there are for any A, B, and C that are not mutually exclusive. So I'm going to look at any A, any B, and I'm going to write, and this is an exercise that you can do, show that this is true. That the content of my belief in A, well, I can look at A or B, or I can look at A and not B. If A is going to be true, either this is true or that's true, because B is either true or not true. So if B is true, A is true only if this is true. And if B is not true, A is true only if this is true. And the same for B. But these things cannot be both true at the same time. So these things are mutually exclusive. So A or B can be written as this, and B can be written as that. So I have AB twice. I can throw one because X or X is just X. And this can be written as A or B, A or not B, B or not A. And these three are mutually exclusive. And I know how to deal with that. For any A, any B. So we know how to proceed. And how to proceed? Well, I know that the phi of this is the phi of these three ORs, and this is just the sum of these three. Okay? And now I sum this 0. This is AB, this is AB. This is the same phi, the same condition on D. So this is 0. So I'm summing, to that I'm summing 0, and then I'm picking up these two. I wrote in red. These two I wrote in blue, and this is left over here. Okay? So, the general case of the sum rule, it boils down that A and B plus A not B, this is AB, or A not B, so this is A. So these two in red are this. These two in blue are that, and this. And you're beginning to sense something like probability theory coming out of this. Because if you don't, then, well, this is beginning to look like, I'm telling you. So I'm not saying probability, because these are not probabilities yet. These are something else. But it looks really nice. Okay, now I'm going to tell you about function G. Breathe, because now it's beginning to look ugly. Okay? Now and these 5 terms, I've just rewritten the same equation, but now I use the rule that I have for mutually exclusive events, assertions, and this is just an OR of that, and this is just an A. And this is just that, and that is just a B. And this is just comes along all the way. Okay? Now we're going to look at this, and we're going to do it like in the following way. I don't know if G depends on the four arguments. I don't know. I don't know G. You see, I didn't know F, but now I know F. I know phi of X of F, but that's okay. Any phi of F, yeah, because I didn't know F. And you see, this is when this is the you have to remember this. Cox. This is the first theorem of regraduation. I can regraduate my beliefs from F to phi. So I'm not going to talk about that. I'm going to talk about this. This is my first regraduation. There's another regraduation still to come. Okay. I don't know if it depends on the 4. It might depend on less. I don't know. I'm going to look at simple cases where common sense tells me that things cannot be such in order to eliminate. So I'm going to look at candidates for G functions, and I'm going to eliminate all candidates that give rubbish on simple cases. Okay? A philosopher at this point might be, oh, these are new assumptions. Maybe, yeah. So this is the general form of the product rule, and I'm going to consider 7 cases. First, where the G function depends only on A given, I'm looking at A and B given C. I'm going to look only at A, only at B given C. This is candidate number 1. Bachelor number 2. It's A given C, A given B, C. And of course, I can change A and B. So there'll be another G2 with B here, and A here. Candidate number 3, it's A, B given A given B, B given A given C, B, A given B. So this is 2, 2, 2, 2, 3, 3, 4 arguments. There is, besides changing A and B and getting another set of candidates which are the same, there's nothing else I can suppose. So you see, I'm not imposing anything. I'm going to check. Maybe all of them are correct, but I'm going to throw away some of them. Okay? So this is the important thing here. You go to sleep, because then you remember at least the first part, according to what we learned yesterday. Yeah? At this point, this is a good point, because this is why some of you didn't go into physics. Okay? So I'm going to look at candidate number 1. I'm saying, I'm proposing to consider the fact that the disjunction, the conjunction A and B is just a function of my belief in A and my belief in B. So imagine how this theory would work. I say, C is the next person coming through the door, and A is this person has a left eye blue and has a right eye brown. It might be possible that it's very likely that people coming through the door have a left eye blue, and it's very possible that they have a right eye brown. But I don't believe that this catches the possibility that, let's see, I'm sorry. Yeah, okay. You see, he doesn't have both eyes, one brown and the other blue. Okay? So this gives me, if I take this as my general and universal way of performing analysis of beliefs, it would give rubbish. Okay? So I eliminate this on the basis that he doesn't have eyes of two colors. Thank you. G2. I'm going to look at a special case and see that it gives rubbish. The next... You were lucky. The next person coming through the door, A is big. B is big and ugly. Okay? So you were lucky. Note that I'm considering a special case. If it gives rubbish on a special case, then I throw it away. A and B is big and ugly, and is big, is the same as is big and ugly. So A and B is equal to B. So phi of AB is phi of B. And then if I use G2, then this is G2 of A given A, and this is truth. So there must be some value for truth, which I don't know what it is, but this is just that. So I have that phi of B is just a function of A and this constant. So if I vary A, yeah, and I'm looking at different things here for which I have different beliefs, this other thing is not going to change. So it says that my belief that it's big and ugly is only a function of my belief that is big. As if all big people were ugly. Not true. So I eliminate this candidate. Just a function of A. So we had 7. Okay. You get a Mars bar if you get me in trouble with this G3. So this is the only survivor that we're going to show. Okay, of the 7 candidates, this is the one, and the one with A and B switched positions. So this is okay. I don't know any example that makes a fool out of the guy that uses this kind of reasoning. If you know something, please tell me. But you'll be famous. Yeah, at least in this small community, yeah, with people who care about this stuff. And now, G4, which is that, and we consider the special case. It has to work with anything. A is equal to B, then AB is equal to A, then A, this is the belief on any A. It's equal to the belief on A and A, or A and B, because they are the same. And this is just a constant, because it's a function of this constant value, which I don't know what it is. But it's a constant. I can change A, and nothing happens. So I have to attribute the same belief to any assertion that I make if I use this G4, so I don't use it. I eliminate that. Okay. To this point, it was easy. Now, I'm going to say, and I'm going to come back to this, is that G phi can be shown to be a special case, either of G1, which I eliminated, or G3, which had G1 and G3 had two arguments. So it's either G1 or G5. If it's either G1 or G3, if it's G3, I already have that candidate surviving, and if it's G1, I already eliminated. So I don't have to look at G5. I'm going to show you that. G6. Well, I'm not going to show you, but it's the same proof, exactly the same proof as the previous case, that G6 is either G3, in which case it survives, but I already know it, or it's G4, and I already eliminate that. And G7 is either G phi, which was G3 or G1, or it's G6, which is G3 or G4. So so I'm not going to show you that, but I'm going to show you how to do that. How to show that G phi is either this or that. How do we do that? Well, this is for those of you that are still paying attention, I'm going to look at this case. The other cases are you proceed in the same way. Okay, let's go. This is something that, you see, when you're lecturing physics, at some point you have to say, okay, no excuses. This is mathematics, physics, I don't know. But no excuses. We have to do it. So, yeah? And you see, at this point, you have to look at me as I'm the preacher. I'm coming here to bring you the word. This is the true mathematical theory you have to use. So you have at least at one point, instead of believing me, doing it yourself. You see, that's the difference between a preacher and a Bayesian. Slight difference is that I'm not asking to believe me. Do the algebra. Yeah? That's a difference. Yeah? Okay. Let's go. I'm going to look at associativity again. I'm going to write things in two different ways. I'm going to impose that I'm not manifestly inconsistent, and I'm going to deduce a functional equation. I'm going to solve it, and that's it. Okay? Oh, no, I'm not doing that. I'm going to do that in the next one. I'm going to show you that this G phi is either G3. Okay, so what I'm doing is writing something that is complex in two different ways. Yeah, and I have, I didn't write 2-3 lines, but A, B, this is a G function. So this is a G function of this part and that part. This G function has 3 arguments. The first argument has to do with this, the second with that, the third with this given this. So the first one is also an A and B, so it's going to be written by a G function. Then the second argument is C, which I'm just calling U. And the third argument is the first argument, which in this case is an A and B, which is also going to be written as a G function. On the other hand, on this side, I have A, which is a simple assertion. And then I have the 3 arguments. But the middle argument, this one, which is the B, is a B and C, which I write as a G function. So I have G of x, y, z, of U, of G5, V, W, S. And here I have X, Y, U, W, S. First thing, note that there is no Z on this side. That's an interesting thing. So if I change Z on this side doesn't change. So this cannot depend on Z. Okay? So I'm going to do the short. I'm a little bit lazy. I don't want to spend 20 pages not assuming differentiability, only to find at the end that the most general solution to that is differentiable. So I'm going to assume differentiability because, you know, I'm willing to, well, I want to be lazy. I don't have time. Okay, that's the answer. So we take a derivative with respect to this value z here because it doesn't appear, and I'm going to use the notation that with a lower index, this is the derivative with respect, if it's k, to the kth argument. So when I take a derivative with respect to g, this is a chain rule for people learn neuroscience and sometimes they don't know calculus. This is really, it's like, yeah, I can build an Empire State, but then I cannot make a sand castle, you know, with my, this is simple. So if any student here doesn't know calculus, that's the best investment they can do. Learn calculus. Anyway, at this point, I have to take a derivative of z, and it's the first argument. So it's going to be a g1 here because it's the derivative of the first argument. And then I have to take a derivative of this with respect to the third argument, so it's a g3. But this is equal to the derivative of this, but with respect to a variable that does not appear here, so this is 0. So I have that a g1 times a g3 is 0 for any arguments. So it's either one is 0 or the other is 0. They cannot both be 0 because then it would be complicated. But anyway, if G1 is 0, it means that it's not dependent on the first argument. So this is just the version of G3. If it's not dependent on this part, it's only dependent on these two, then it's G3. And if it's independent of the third one, this is just a function of A and B. So that's G1, which we already threw away. So at this point, what I'm saying is this is 0, or this is 0, or that is 0. In this case, it's G3. Doesn't depend on the first one. It's G3, but it's G1. So G5, it's thrown away because it's already included in G3, or not in G. It has been eliminated. So what we left with is that essentially we have only two candidates and no arguments to throw this away. So G3 is, now I'm going to lose the 3 because 1, 2, 4, 5, 6, 7 were thrown away. I only have G3. It's only G. No more G3s. So what I'm telling you is that the conjunction A and B, the phi of that, the monotonic function phi applied to this number is G of, and look how interesting this is. If I want to know the truth value of A and B, I should first look at A, and then if A is not true, I'm done with it. A, B cannot be true. But if A is true, then I consider A to be true, and then I look at the case whether B is true in the condition that A is true. But I can do the other way around. I can start looking at B, and given that B is true, I can look at A. So that's the result of this analysis, is that I cannot find any problem with that. It's not that I have proven that this is correct. I'm not proving that. I'm proving that any other thing that I do is wrong, at least in some example. So I threw those away. So this is not a proof by deduction. This is a proof by elimination of all the other possible candidates, which reminds me of elections in some places. Yeah? You kill all the candidates, I win. Okay? But consistency tells me that if I analyze the same thing, these two things have to be the same. Okay? With a problem, I don't still know G. So the next problem, if you're still awake, is to calculate G. Okay. I'm going to look at the distributivity of A and B or C, which can be written as A or B, or A and C. So this is true only if A is true and B or C is true. So it's either that A and B is true or that A and C is true. A always has to be true, but I can live with only one of B and C, but if both are true, then it's okay. So I'm going to look at the phi of this, and this is the phi of that. I'm going to look at the case. I know how to treat OR functions. I discovered the value. I discovered how F behaves. Can I use this for things that are not mutually exclusive? No, because if you go back, a lot of... I had this here, and I don't know how that works. So I cannot use this. Although I know it's contingent on the fact that I know how to do that, which I don't at this point. So I cannot use this for any A and B. I have to go and do it for only these mutually exclusive. So B and C are mutually exclusive in the context of D. They can be not mutually exclusive in another context, but on D, given D, they cannot be true simultaneously. Okay, So if these are mutually exclusive, I know how to do that. Okay, this is a G function because it's an AND. Here's an AND. And this is, so, of that. And I know how this works because these are mutually exclusive. So this is just the sum of this. Yeah? This is the right side. Yeah? And now I have to look at from here. That was the left. Yeah, that's my problem. I never know. Yeah, okay. Thank you. I have to. I'm not wearing a watch, so I don't know which one is. Okay, so this was the left side, and now I'm looking at the right side. Okay, and the right side is a disjunction of two mutually exclusive things. So I know it's just the sum, but the sum of what? Of conjunctions. So for this, I use G. So the left side is a G of this form, and the right side is a G, is a sum of G's. Because it's a phi plus a phi, this I know exactly. And this is a G, that's a G. So if you substitute all this by simple letters, I have that G of x, y plus z. You see, it's a function of something, comma, the sum of two things. So it's something, comma, the sum of two things, equal to the sum of two things, which are G functions themselves. So this is my functional equation that I obtained here. Okay. So what do I know about this type of equation? This is what people call linearity. You see? I discover that on the second argument, this function G is linear. So the function of the sum is the sum of the functions. Fix x, this is just a function of one argument, and it's linear on that argument. So if it's linear, I can write it like something that depends on x plus something that depends on b. This is the equation of a linear function of y. I substitute this into that equation, and on this side, I have a plus by plus bx, because it's linear in y and x. And on this other side, I have a plus by plus a plus bx. So on this side, I have two a's, and on that side, I have only one a. So a has to be 0. Okay? So a is 0. I discovered that my linear function is just an unknown function b of x times linear part. Okay, so my product rule, candidate number 3, is written in this very simple way. Now, this was done for a special case of mutually exclusive assertions, and now for A and D given D is exactly A and D. So now I write, for any A, I write this, and I get that, and I prove that this is, well, I use G, phi of A and D, and the second argument is D given A given D, but this is true, so this is a constant. So this is the second argument. So if this is B times Y, the second argument, this second argument comes here, and I have the B function. But so B of X is something that is X, which was what I'm getting lost here. Okay. Okay. Yeah, this is, I just throw it to the other side. I'm sorry. If you looking at too close and speaking at the same time, you're going to think. So b is that divided by this, which is what I've written here. So at the end, I get that g of xy is xy divided by some number that I don't know. And we get into the end, to the second Cox regraduation that says, look, if I have my phi's, which is a monotonic function of some numbers which I don't know, and I divide by this number, has to be different from 0, otherwise it would be the same value of as false. So truth and false have to have different numbers in order to make sense, so this cannot be 0, so I can divide by it. Okay, if I divide by it, I can regraduate my beliefs, which were regraduated by phi, by this number. So now I'm getting this object here, and now this deserves to be written as a p, because at the end is going to be probability. Okay? So instead of ordering beliefs given by an unknown number, talk about an unknown monotonic function of an unknown real number and divide by something else that you don't know what it is. But these things have the following characteristics, that for anything that is absolutely certain that it's true, the value is 1, and if it's false, the value is 0. This I could not escape. It could be infinity, but I chose to be 0. And this I just regraduated, and it's 1. So it's starting to smell like probability. Now I go to phi, and I write that, well, if G is this, the phi of this conjunction is that. And if I divide again by phi of t here and phi of t here, I get this equation. And since I define this regraduation, this is p, and p of the argument that is there. So at this point, you see that p of a and b given c is p of a given c, p of b given a, c. Or I could start with b and write as p of b and p of a given b. At this point, you have to agree this smells like probability. Actually, if I impose consistency, because this have to be the same number, I get Bayes' theorem. So Bayes' theorem, when people talk, oh, I'm Bayesian, why? Because I believe in consistency, because I want to describe things with numbers, because I believe that assertions that are built by connectives like or and should be a function of the simpler beliefs that I have of the beliefs I have on the simple assertions. That's it. And then, of course, you might choose not to regraduate. You can. Nobody's going to read your papers. That's simple, because the algebra is going to be so complicated that you regraduate in order to make life simple. And what you get is exactly probability theory. Now, at this point, I'm going to go back to the problem that I described for the rain case. A is it rains. B, there are clouds. And the question was whether it's more likely to rain if there are clouds. What is my belief in it's going to rain, or it rains, given that there are clouds? Or what is my belief in there are clouds, given that there is no rain? And I told you, yes, you should believe these things, because that's what your mother told you when you were leaving home, and take the umbrella because there are clouds. But you would tell her, no, Aristotle would say that logic, this is not a logic statement. We're showing you that your mother was right, yes? That she, you see, she has this extension of Aristotelian logic that came from millions of years of evolution. We had to solve problems, we had to make sense. So inference is what we do, and we do it beyond Aristotle. Okay, I'm going to use this. The value of that something is, I'm certain that is false, is 0. This is what we proved. And the value of certainty, what is this? This is It rains if there are no clouds. I'm certain that it cannot rain if there are not clouds. So this is 0. And this is, if it rains, I'm certain that there cannot be clouds. Yeah? So this is 1. And then, what is my belief that there are clouds? This is P of there are clouds, given C. This is all my knowledge about climate. And this is between 0 and 1. Sometimes there are clouds, sometimes there are no clouds. My belief, well, I don't know. It's some number between 0 and 1. It's in my order of beliefs, I have 0 that there are never clouds, 1 that there are always clouds, but I know I'm in the middle. I don't have any, but it's something in between. So I now use Bayes' theorem, and I say, what is the probability? And I'm not making any excuses now. I say probability that it rains, given there are clouds, and I write Bayes. So I analyze this as the probability of raining times the probability that there are clouds, given that it rains. And this piece came from the other side, and it's just the probability that there are clouds. And now I'm going to substitute this number that is 1. So this is 1. I can throw it away. Just 1. So that's why I don't write it here. And I'm going to substitute this in the denominator by the larger number, 1. So if I substitute something in the denominator by a larger number, the fraction comes down. So this is the probability that is left. This is just this term. And this is the probability that it rains. And this is the probability that it rains, given the fact that there are clouds. So yes, according to the theory that we have developed, if there are clouds, the probability of raining is larger. Voila, you learned something, yeah? You cannot go back from this, I'm sorry. I mean, once you've seen the light, you have to agree that, because if I don't do this, then I'm violating one of the desires. And do I want? I might want to trick people. I might have, but if you want to do science, then you don't want to fool yourself. So yeah, this is. So what is information? Now I started, information. What is information? Information is something that changes our beliefs. That's it. Information is not 2 bits. Things like Shannon. Shannon is information for engineers. Very important. But as a neuroscientist, you might be willing to give different values or different names to things like you have a Shusha program in the TV or you have a BBC documentary. The same number of bits, but different information. Because one is going to change your beliefs, the other is not. Yeah? So information is, B is relevant information for A if my probability of A given B is different than the probability of A given C. You see, I change my beliefs to probabilities, but still these probabilities are regraduated numbers that do not change the order of my beliefs, and they have rules that I can come back and check against Kolmogorov. So this is Kolmogorov, and I see that it's in Portuguese, so it doesn't make any difference. Because I picked up from lecture notes that were in Portuguese. But what you know is that there is a universe, and E is a collection of elements, which are our assertions, which are, that's it, elementary events. And we call assertions in our case. But F is the set of all the subsets of E, and the universe, it's one of the elements of the set of all the subsets. It's a sigma field. Yeah, that means that if A is in F, not A is in F. And F is closed until under countable unions. And there exists a function. This is a mapping from events, yes, which are assertions in our language, to a measure function, something that is between 0 and 1. And this function is 1 for everything, which means, yeah, this is exactly the truth value. And then this function is always positive. It's between 0 and 1, yes? If two assertions are mutually exclusive, yeah, has no elements in common, then the P of A or AI or AJ is just the sum of the probabilities. And this is everything we discovered in the previous transparencies, except for the most important thing that I think that you should remember, that is Bayes' theorems. It's the most relevant for your work. Kolmogorov did not invent probability theory. Probability theory was old when he came. What he joined was, he didn't invent measure theory, but he saw probability. Oh, look at this, measure theory. And yeah, measure theory is a particular instance where probability is a good language. So he said, these are the axioms of probability. Well, yeah, true. But there are things that cannot be integrated in the usual sense of Lebesgue theory and things like that, that you can still talk about probability. So the framework I'm saying, although it doesn't look as so impressive, I mean, if somebody tells you that something is a sigma field, then yeah, you should say, yes, I'm not arguing against that. But what I told you is something that is larger than Kolmogorov. In the sense, it's equivalent to Kolmogorov, but it gives me the confidence to deal with things that are not integrable in the same sense. Yeah? What is my belief that the smell of the flower would be the same if the name of the rose changed? Do that with Kolmogorov, yeah? So, you see, Kolmogorov published this, and a few years later, Rao, another probabilist, said, yeah, you forgot about conditional probabilities. What I told you is that there are no probabilities in my world that are not conditional. Every probability is conditional. On what? If I get the coin again, and the probability that I will use to describe my belief that the coin will come up heads, yeah? That's something that depends on the experiment. It's conditional on the experiment I'm going to make. So every probability, there's no, if you say, no, but the probability that a hydrogen atom will decay is given by quantum theory. Well, under what conditions? If I put my atom in a metallic box this size, some modes will not be allowed by the cavity, and the probability that will decay changes. So I can trick you like I did with a coin and change probabilities even in quantum mechanics by changing the experimental conditions. So what is the probability? Well, the probability is what I attribute based on the information I have. And you said, yes, but how does the hydrogen atom know about what's in my head? Well, the hydrogen atom does not know, but what's in my head might be relevant or not for describing those experimental results. If I'm doing a good job, then what's in my head is going to be better. If I do a lousy job, it's going to be bad. And that's bad theory, good theory. So the atom doesn't care what I'm doing, but I, as a theorist, I do care in throwing away theories that are not good enough to talk about the physical system. Okay, now let's go back to something you all know you learned in high school. This is a Venn diagram. And I could have started like this. And I said, I'm going to throw darts in this universe, and some of those darts are going to fall inside a number NA. I'm going to throw NE, and some of NA are going to land in A, NB are going to land in B, and some are going to land in A and B at the same time. So NAB over NE is something that I can write like NAB over NE, NAB over NE. And now, this is a very common argument. And now I divide and multiply by the number that came in A and the number that came in B. And you see, this is the fraction that having arrived in A were also in B. So this is the conditional of B given A. And this is the conditional of A given B. And this is just the probability that it lands in A. Well, not the probability, the fraction. Yeah? So I could write my Bayes theorem just from the equality of these two things. This plus that. And some people are happy with that because probabilities are just the fraction of times that something happens. And this is something that I want to tell you, no. 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 Probabilities are something. The frequencies that something happened is something else. That something had a frequency over, that's data, that's information, that's an assertion. Suppose I get now a coin, I throw it, it hits the ceiling, it comes down. And I throw that 5,000 times. That's a frequency that I can count how many times it came tails, how many times it came heads. Is that probability? Is the probability that it will land on the head equal to 1/2? I have another coin here if you want to keep playing. I bought this in Las Vegas. Are you willing to play this game? You see? How am I going to be able to bet on the outcome of natural experiments if I don't know any frequency? You see, frequency, if I throw it 10,000 times, I can say that frequency will converge to the value of the probability. But always converge implies in that I'm using some measure of distance between two things. And what's the precise meaning of the word converges to probability is that it converges in probability. That if you make different experiments, all of you will get different frequencies that will, in probability, this is a random variable, converge in probability to the probability of the coin coming up. So if you want to define probability, you cannot use frequencies because you have to use probability to say that frequency converges in probability to the probability. So it's not a very good thing to define probability using frequencies if you don't know what probability is. Yeah.
It's the same as saying that induction converges to deduction. That by observing many times.
Well, it's not exactly what I'm saying, but I agree that if you have a lot of data, your subjectivity in the prior goes away if you have consistent data being accumulated. So the more, so this is, I don't want to be Bayesian because it's all subjective. Okay, tell me of some human endeavor in which you don't use the brain. Yeah? Everything is subjective. But subjective doesn't mean that I am free to believe as I like. If he does the experiment 100 times, I do the experiment 100 times, and we do not have the same subjective beliefs, something is wrong. So it's very objective in the sense that I have to do this, and then my subjective beliefs are that. But we will agree if we are willing to be reasonable. Yeah? So it's... So the exercise for the students is come up with 5 reasons why this is not a good deduction of Bayes rules, why I gave you a much better deduction of Bayes rules. But this is something you teach in high school, and it's okay. But it's not. This is not the whole story. Things are not darts that you throw. If I'm talking about the mass of Saturn, which was the first use of Bayes' theorem, there are no NA masses of Saturn? There's only one Saturn. It's not a random variable that jiggles about in time. It has one value. What might jiggle in time is my belief that the value of the mass of Saturn has one value or another. So it's information that I have from the belief in Newton's theory and from the measurements that I've made that tell me how to believe in different assertions. That is, the mass of Saturn is in this region or that region or that region. Then I have a distribution of beliefs. Okay, exercise. So this is, you see, this ends with the probability theory. Now a course in probability theory will go to, yeah, you have to learn how to use it. You have to learn how to calculate things. You have to do stuff. Yeah. But we're going to do exercises. What's the time, actually? 15 minutes. So I came to the first third of my talk. Anyway, this is the important thing. Yeah? Okay. This is very, very simple. But this is probably something that you know. I took a test for a disease, and I'm going to use the assertion capital R is little r if the test is positive, and it's R bar if it's negative. And the test was positive. What do I know? I know R. Do I know if I'm sick? That's what I want to know. I want to know if I'm sick or if I'm healthy. So what I want to do is to calculate what's the probability of being sick given on the condition that the test was R. Yes? Well, I asked the doctor, and he told me that the test is very good. If you're sick, the test will come out positive 95% of the time. So does that mean that I have 95% of probability of being sick? No. Look, the notation that I'm using is very clear. Always write what you want to know on this side, condition of what you know. And then, but this is what I want to know. What the doctor is telling me is other thing. It's another thing. Not totally different, but it's not the same thing. It tells me that if I'm sick and I take the test, the probability that it will come out positive is 95. So what do? I apply, of course, what you have to do when you go to the doctor is apply Bayes' theorem. That's obvious. Yeah, I know this, I want to know that. Look, what do I have to ask? Well, theory guides you in what you have to ask. This is not something that, yeah, I ask any question. No, I want to know that, and I use Bayes' theorem, and I write it as P of S, and then given that S is, oops, this is wrong. Given that S is sick, then this is the probability of the test being positive. Yeah? And this is the other probability, which is a complementary probability of not being sick given that the test is that. So Bayes' theorem allows me to write these two things, and I just do the ratio of these things, and note when I do the ratio, this denominator is the same, so it cancels out. So what I learned is that the probability of being sick divided by the probability of not being sick under the same conditions is this. And what I asked the doctor is that it's about this too. So this is 95, this is 19, and I'm left. I want to know that, but I'm left, I cannot answer. I don't know this. So you see, theory asks you into asking, demands that you ask, what is the prevalence of this, in the group that take the test, what's the prevalence of this disease? So 19 is scary, it's a big factor, but maybe it's not so much. we have to look at this prior information that we have before we know the result of the test. Okay? And suppose now that this is a very uncommon disease. And only 1% of the people that take the test really are sick. So now I have information for this is a small number, this is a large number, 0.01, 0.99. So it comes out that the ratio of probabilities is this, and that my probability of not being sick is not so small, it's 84. You see? This is just a very simple example that I guess most of you have would know what to do. But this is not what sometimes people really forget about the priors. You see, Bayes' theorem, which is consistency of the product of something given something. And now these somethings I'm going to give names. This H I'm using because it's a hypothesis that I make about something. And D is the assertion that I measure under conditions I something, and it came out as some data. So what's the probability of the hypothesis given the data? And Bayes' theorem tells you it's the probability of the hypothesis in the absence of data, but with all the theoretical knowledge that I have, times the probability of, given the fact that there's an I missing here, given that the hypothesis is true, I would observe the data. This is the likelihood, and this is the prior. This is called the evidence. So, you see, I've been telling you about rain, I've been telling you about medical tests, but this is really much more important. I could be saying that I'm talking about the comparison of Maxwell electromagnetic theory given the data of the experiments that I did in the lab. And you see, this is something that philosophers of science are starting to use in order to gauge whether this theory should be accepted or not. It can also be the fact that suppose that I have a model that tells me, given, imagine I have a brain here, and there is some state of the world outside. So this agent has some senses, and information comes through the sense, and it establishes some state in the brain. And this is the state of the brain. And this is the probability that this cognitive system will attribute to the state of the world outside, given its internal state. And I can write this as, what's the probability of the state outside being H? And what is the probability that my senses, or the senses of this cognitive system, would give rise to this internal state, given this external state? So you see, I can use this to model lots of things. This is the beginning of modeling an infinite amount of problems. So in that sense, I feel like this preacher that comes here and brings you the word. Yes, this is at least the starting point for many, many, many problems. Suppose I have competing hypotheses. I have H1 and H2. I write Bayes' theorem for H1. I write Bayes' theorems for H2. And I have that the ratio of H1, of believing H1 against believing H2, given the same data, is the ratio of the likelihoods times the ratio of the priors. So this would be like a likelihood test if I believed a priori the same for H1 and H2. I was willing to make some bad comments about p-values, but I think p-values are going the way they deserve in a few years. It used to be, you see, the coin has this God-given value of 1/2 that it will fall tails or heads. I show you this knot. And p-value is equal to 0.05 is also not a constant of nature that should be believed. Yeah? Really, p-values are really going away. Why? Because people are going to die. The people that know about p-values. And people, you see, I was going to show you, I didn't do it. There's a graph of how many times Bayes is being mentioned in the literature. It has an explosive curve going up in time. Yeah. Mauro, we're getting old, so I'm going to use a few last minutes to say things like, when I was a Bayesian 20 years ago, people in statistics, used to look at you and say, Bayesian, you're subjective. Oh, poor you. Yeah. Okay, these people have now, they retired. And there's some of them are still there. And they say, wow, so you were talking about Bayes. Yeah, it's like a surprise. So the only thing I want to do is live a little longer in order to see more people coming and telling me these things. So if you believe in p-values, go and think again about p-values. If you think that, yes, my p-value is 0.01, I should publish, go again, go back. I'm not going to, I'm just telling you, this is not, in my church, this is not welcome. Yeah? P-values are not, really, p-values are going down the drain. Well, you see, now I'm going into applications. The idea that the prior is important, you can do two things at this point. Once you said, yeah, I'm not going to be a Bayesian because I have to put my subjective priors into that. Well, there's a lot of theory about subjective priors. There can be objective priors. They are entropic. You can deduce something when you don't know anything. The fact that you know a likelihood function should tell you what to believe before you start doing experiments. So there's no vacuum of information. If you're going to do an experiment, I'm going to measure something. Well, you have to know at least where the brain is. Yeah, you always have some background data that comes from, and so you always have some prior information. You either not use it and say, no, I'm not using likelihoods because I'm using a likelihood ratio, but that is not using any priors, because that is acting as if you assign the same prior to the two hypotheses and just cancel it out and look at the likelihood ratio. So not using priors doesn't mean that you're not using priors. It means, for any statistical test, it means that you are a Bayesian. It's not you're a Bayesian. You're acting as a Bayesian would act if he had this given information. So if you only do a likelihood test, you're behaving like a Bayesian that assumes the same prior information. So it's not that you're not using priors, you're using it without knowing. And it's better to know than not to know. Okay? Also, the second thing is that, well, if priors are here, then let's do some effort in going out there and finding prior information. And this is something that we've done. We're looking at cortical areas that are active during some cognitive process. And we solve the inverse problem of given electroencephalographic information, the time series of voltage. We can solve the problem on different scales, and we have, and this is a word for physicists, something like an inverse renormalization group transformation from one scale to the other. And we can we have a posterior, and this is, well, this is, you do a problem on a given scale, you find a posterior. You solve the inverse problem. You have a posterior of activity on one level, and you use that to calculate a prior distribution on a finer scale. And so you can solve this. And by the end that you get here, you have a prior information that is very precise. And so the inverse problem is very easy. So it's not that prior information cannot be. You can define random variables in one scale and another, and this can give some prior information on that. And then you use some, I don't want to use the word, but I'm going to use it. It's entropic inference, which is related to Bayesian. But you see, if you believe that, yes, this is true, and I should go and look at prior information, then you always win. Instead of just putting it under the rug and saying, I'm not subjective, I'm not going to be that kind of person, and throw it away. So I'm going to use it, and I'm going to actively search for better prior information. Okay. So now I start the second part, very, very rapidly. The question is, I gave you arguments for believing that the theory that I should use is probability. And if you have some prior information, how do you turn that when data arrives into posterior distributions using Bayes' theorem? But information comes in other ways. And we have to design a method that allows for a systematic search of the preferred posterior distribution. And this is going to lead into, when information comes in other ways, to a variational method in which I'm going to rank all candidates for the distribution of my beliefs, and I'm going to rank them according to preferences. So now I'm going to give not preference, I'm not going to rank beliefs, but I'm going to rank distributions. So I'm going to assign a number to every distribution of probability, and I'm going to design a method which is going to turn out to be a variational method, and it's just maximum entropy, in order to assign and update probabilities when new information arrives. So I have, look, I'm going to find here, I'm going to assign to every distribution a number. That's a functional. To every function a number, that's a functional. And different functionals give rise to different entropies. And I'm going to argue that there's going to be just a single surviving candidate for this functional, which is entropy. And it's not that it leads to demonstrably correct inference, but rather that all other candidate entropies fail to perform as desired. So I'm going to throw away different ways of updating probability which are not complying to very simple desires. The desire number one is that my method of attributing probabilities should be universal. If I don't know anything about something and I'm going to do inference, I shouldn't be able to choose my method, because for this method, this is the good inference that I should use. If I don't know I have to do inference, then how do I know what the method is? Beliefs, it should be parsimonious. Beliefs should be updated only to the minimum extent. I'm going to go quickly because otherwise I don't have time. So I'm going to do the slightest change. When the information comes, I believe something. Information comes, I'm going to change my beliefs. I'm going to make the smallest possible change in some sense. If nothing happens, I will not change my mind about my beliefs. So prior information takes priority. In the absence of any evidence to the contrary, there is no reason to change my mind. This is, you can do other stuff. I think this is reasonable. If I have a physical system and I make a change of coordinates, you know, a coordinate is just a name I give to a point in space. If I make a change of coordinates, it's just another name. My decisions, my inference should not depend on that. Decision theory should not depend on the names that I give to the degrees of freedom. And then finally, and very important and sometimes overlooked, is the fact that I want to treat independent systems as independent. Suppose that I have a coffee pot here and I have a star on the galaxy X9, and I do my inference on the assumption that the star exists, and I do inference about this coffee pot, and then I do inference about the coffee pot under the assumption that this star does not exist, I have to get the same result. If I don't use this entropy, I can do astronomy by looking at the coffee pot. Not very reasonable. Okay? So that's why I say that I only have one distribution, one entropy. And to many people coming to Brazil, this might sound a little bit surprising, because if I use other entropies popular in this land, I'm going to be able to do astronomy looking at a coffee pot. Okay? So I'm not willing to do that. You might, but I'm not. And the thing is that what you end up, I mean, if I started the lecture saying that from those blah, blah, blah statements I get a theory, you would not believe me. But I did that for probability. And now I'm telling you that from this blah, 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 and I challenge you to tell me which of these you don't like, I get that if I have a belief and I receive new information which eliminates a family of distributions which do not satisfy this incoming information, then I'm going to attach a preference to every distribution of probability given by this number, which is an integral over all the variables, p log p over q. And this is the entropy. This is the entropy. And this is the blue thing. Only functional that does not violate the desiderata. Okay? So this is also in my preacher book. This is the second law. Okay? Use probability theories. Do not believe. You cannot serve two entropies. Yeah? That's the word. You cannot serve two entropies. So this is a space in which every point is not an X. By a point in this space, I mean a distribution of probabilities. So I believe this. Now comes information that says, look, I did some measurements, and for example, I should be here in this region. Yeah? But I had at some point information that led me to that. So now I can update using maximum entropy. And the interpretation of maximum entropy is minimum distance. It's like entropy in here. This is like a distance between Q and P. Okay? So in this space of probability, this is the directed distance of going from here to here. You might say, oh, this is not a distance because it's not invertible. This is not the same going that. Look, I live in São Paulo. If I want to go from here to there, sometimes it takes 5 minutes. But then I have to come back. I have to go all the way. And are you telling me that I cannot use the distance, that this is close? If I'm here, this is close. But if I'm here, this is far? I use it every day. I talked to a taxi driver, and he says, no, the distance is short, but if I come back, it's long. So, no, you're being inconsistent. He will open the door and tell me, leave. I don't want to take a... Huh? So the thing is that this induces a geometry, which is extremely interesting. But I don't have time to go there. Suppose this space of probabilities is parametric in the sense that every point is, for example, a Gaussian. Each point is a Gaussian, which is, so I measure, for example, mean and variance, or it can be more higher dimensional. Yeah. So look, if I have information and this brings me there, I can say there's an update of the weights of this distribution, and I come here. And this is the basis for learning algorithms in neural networks. So the change in parameters in the manifold can be mapped into These are approximate algorithms for neural networks that come from entropic arguments. So you can use these for cognition modeling in neural networks. What else? If information comes in the form of data, I measured X and it gave me 2. This is data that you can use in Bayes theorems. You can use it in maximum entropy. It gives you the same result. You go from one prior to the same posterior. From the same prior to the same posterior using Bayes or maximum entropy. This is an important result. If you look at you can look at interactions of variables because you can look at the joint probability of X and Y, and you can look at the marginals. This is just integrating out, summing over all possible values of Y, and the marginal of P of Y integrating over X. And you can, if you look at the entropy of P of XY as the posterior and P of X, P of Y, this gives you this is the mutual entropy, and this is just a distance in the space of distributions of probability of something that is describing you something like the interaction of X and Y. Yeah, it's not a correlation exactly, but it's not. It's a mutual information. So this is the interpretation of mutual information is the distance between these two probabilities. It's like Shannon entropy. You see, this is Shannon. This is not Shannon because Shannon doesn't have a Q here. Well, actually, Shannon has a Q, which is the uniform distribution. But he didn't write it. So this is like the distance. You see, if I write P of Q from the uniform distribution, it's just Shannon plus a constant term. And for the physicist, this is exactly the entropy that Boltzmann did in the microcanonical ensemble, which has nothing to do with what I'm saying. Comments for physicists. So Boltzmann is just a special case. Statistical mechanics is a theory of inference. It's the first theory of inference. And that's just, people discovered this without realizing they were doing inference, except that Laplace and Bernoulli and Maxwell already wanted to do this. There are other variational theories which have been written as maximum entropy theories, which is just, somewhat important. Newtonian mechanics, quantum mechanics can be written as a theory of inference. Physics, in this way of looking at things, is not about what it's not about reality. Physics is not about reality. Physics is about what we can say based on information about reality. Different, slightly different, but very important. So every variational theory, several, we are in the process of working this kind of thing. They come from the variational principle of maximum entropy. The Newtonian mechanics can be written as a least action principle. It's a variational principle. It can be derived from maximum entropy. And the question is, this is some kind of optimal inference in some technical sense, but why do we make optimal inferences in physics? Well, maybe because we evolved by solving problems, and this has to do, eventually, you see, all physics will boil down to deriving from evolutionary arguments what is the good way to make inference, and from once we have the engine of inference working, given relevant information, we can deduce the dynamics of that. So just this is not a lecture anymore. This is just like propaganda that, read the book. Yeah? Okay, so this is the recipe that I leave you, and this is what I do. You identify, you're going to study a problem. You identify the degrees of freedom that are relevant under experimental conditions. You attribute a probability that is prior to anything that you measure. Could be uniform, but if you don't do anything, you're doing something. If you forget about prior distributions, you're doing uniform distributions, which is something that you should assume. I'm doing that. You identify functions which are, well, constraints. This I translate from Portuguese. This is not, yeah? Constraints. You identify this, and then you update probabilities using maximum entropy. And this is just an example of why, and you're going to see Galvez coming here on, and he's going to tell you, I'm going to do Gibbs-Boltzmann distributions. I don't know why, but that's what I do. He told me once that. I think you were there, and I said, well, I gave you all this 2-hour talk in order to say, yes, this is what you should do. So Galvez, you pay attention to what he's going to say, because he's doing the correct distributions. If he doesn't do that, then ask him, why are you not doing Gibbs? Okay. Then you calculate order parameters. This is things that you can, this is thermodynamics. The order parameters are things that have an interpretation in thermodynamics. And you see the talk that was given yesterday was about this kind of thing. And then as a scientist, you should always, well, try to look for empirical data. And I say this entropy is not a property of the system, as you might think. Entropy is something that characterizes the state of knowledge that the scientist is in. It's conditioned on the available information, so it's subjective. Okay, now we enter into the end. Okay, I was going to talk about how do I discuss social organizations, moral foundation theory. This is all beta-driven analysis of social inequality and of moral. Okay. He told me that I would have 3 lectures several months ago. That's his fault. I have the email.
I have different priors.
Thank you.